In this video, I'll show you how to solve the ALEKS problem called Solving Applied Mass Percent Problems. I have found at least 5 different versions of this problem, and in this video, I'm going to go through all 5 of the versions that I found. So if you're looking for a particular variation of this problem, just start fast forwarding until you find it. This first problem that we're starting with is asking us to calculate what is the mass of a pure element. I have iron in this particular problem. What mass could be extracted from the compound Fe3O4 given that we have this much of the compound, 4 kilograms of that Fe3O4. Don't confuse this problem with this one, which looks really similar. This one is kind of the opposite situation. It's saying, okay, if you wanted to extract 5 kilograms of pure gold, the element, then how much mass of the compound would you have to start with? So they're similar, but not exactly the same. We're going to do this one first. So the first thing that we want to do is recognize that the ratio of the iron atom in this Fe3O4 compound is a constant. It doesn't matter how much of this sample we have, 4 kilograms, 10 kilograms, 2 grams, it doesn't make a difference. The mass percent of the iron in the Fe3O4 is going to be a constant. So our first job is to figure out what that mass percent is. We're going to set up an equation where we're going to calculate the mass of all 3 of the iron atoms, because we've got 3 iron atoms in this molecule. We were going to calculate the mass of all 3 iron atoms relative to the total mass of the compound. I'm going to use the periodic table. That's the atomic mass of iron. That's the atomic mass of oxygen. I'm multiplying this by 3 because there are 3 irons in the molecule. I'm multiplying this by 4 because there are 4 oxygens in the molecule. So again, this is going to give me the total mass of the 3 iron atoms per the total mass of the compound. Here's the math worked out. This is just the 55.85 times 3 total mass of the compound. Now again, this, as I said, this ratio is a constant. The mass of the iron per total mass of the compound is constant no matter how much of this compound we have. So what we can do is take this relative ratio and we can set it equal to any mass that we want. Which is what I've done here. So I'm saying here is my constant. This is my constant ratio of iron to Fe3O4. What if, as the problem is saying, what if I had 4 kilograms of that compound? I could use this relationship right here. So now we're not worried about this stuff anymore. I can use this relationship right here with some algebra to solve for the mass of iron. So I'm just going to use this cross multiplication rule and set up this equation. 167.55 times 4 kilograms is equal to 231.55 times that unknown x. I am going to isolate that unknown x variable by dividing both sides by 231.55 and solve for x. ALEKS is pretty generous with the sig figs here, only wants 2 sig figs, which gives you quite a bit of room for rounding. Now for the other version of this problem, which is basically kind of the opposite situation, we're going to start by setting it up the exact same way. So this problem is asking me about gold in AuTe2, which means I want to figure out what is the relative mass of gold in this AuTe2 compound using the periodic table. That's the atomic mass of gold. Atomic mass of gold, that's the atomic mass of Te. I'm multiplying it by 2 because there are 2 of them. This is going to give me the ratio of gold per AuTe, the ratio by mass. Now in this problem, I know the amount of pure gold, and I'm trying to figure out what mass of AuTe would give me that 5 kilograms of pure gold. So I'm setting this portion of the problem, I'm setting it up a little bit different, because in this version of the problem, I know that I want 5 kilograms of pure gold. I'm trying to figure out what value of x is going to give me that 5 kilograms of gold. So once again, I'm just using the algebra cross multiplication rule to set up this equation. I'm going to isolate the x variable and then solve for x, 11 kilograms. These two are definitely the easiest versions of this problem. It's just going to get harder from here. So for this problem, we have a lot of information that is not necessary. You don't even really Please don't even waste your time reading this. This is saying that we have a compound C12H22O11, and every time I looked at this problem, it was the same molecular formula, so hopefully that's the case for you if you're looking at this version of the problem. And it's saying that I have 300 grams of this substance, and it wants to know how much water I could get out of that substance. Now, I do want to add, just kind of as a side note, for this molecule, it decomposes into 12 carbon atoms and 11 water molecules. That's part of this story up here. All of the hydrogen and oxygen in this molecule end up becoming water. So, once again, because this is a mass percent problem, we want to set up a ratio that gives us the relative mass of the hydrogen and oxygen. This is basically the relative mass of water that we can get out of this molecule per mass of the molecule. We're going to use the periodic table to help us add this up. We have for the mass of the hydrogen, we have 22 hydrogen atoms. They each have an atomic weight of 1. We have 11 oxygen atoms. They each have an atomic weight of 16. And then down here, here's our total mass of the compound. We have 12 carbon atoms. They each have a mass of 12. There's the 22 hydrogens. There's the 11 oxygens. This is our relative mass of hydrogen and oxygen, aka our relative mass of water per mass of this molecule. Now, again, we're trying to figure out what are we trying to figure out? Trying to figure out the mass of water that we could get if we had 300 grams down here instead of 342. So we're again setting up another equality where we have 300 grams. What would x be? Solve for x. Same type of thing. We're going to use the cross multiplication rule. I'm not taking up as much space now because this is the third time we've seen it. We're going to solve for x, and we get 174 grams. And the problems just get harder after this. So for this one, you have a hypothetical fertilizer, and it's giving you the formulas of 3 components. And it says you've got some inert ingredients that you don't have to worry about. And it's giving you the percent by mass of all 4 of these different components. Every version that I saw had 4 components to it. And it wants you to figure out what percent, again, a lot of words here, but it wants you to figure out what percent by mass, the percent by mass of the nitrogen atoms are in this combination, just the nitrogen atoms alone. So this is tricky. Now, one thing I do want you to pay attention to, of course, you're probably expecting that these numbers are going to vary from one problem to the next, but one thing I didn't expect is that the molecules vary as well. So if you're looking at this problem, a lot of them start with this, but then they mix it up underneath. So don't assume, if you're solving this problem, don't assume that you have the same ingredients as I have on mine, as this is just a really tricky problem. Okay, so again, this is another mass percent problem, but instead of 1 mass percent problem, you're going to have maybe 2 or maybe even 3. Every single one of these molecules that has nitrogen in it, we have to treat each one of those as its own mass percent problem. So you're going to have to do it for at least 1. I have to do it for 2 because I've got nitrogen in my second one. And it's possible that you might have to do it for 3 as well if you have nitrogen down here. But it's okay. We're going to set this up basically pretty much the same way as we did the first 2. We are going to try to make this part a little bit easier. We're going to assume that we have a 100-gram sample of this fertilizer. And we're going to say, okay, we're going to start with this one. For just this part right here, ignoring all the rest of the stuff, let's figure out what is the mass of nitrogen that we have in this much of our 100-gram sample. We're going to start by setting up that ratio of nitrogen to ammonium phosphate. Just like we did with the first 2 problems, we're going to set up the ratio of nitrogen to whatever this molecule is. So what I've done is realized that I've got three nitrogen atoms in this molecule. The atomic weight of nitrogen is 14. So there's my total mass of nitrogen, and then I'm dividing it by my total molecular weight of NH3PO4. This is giving me the ratio of nitrogen to that compound. And then I'm going to set this equal to, now this is going to get a little bit weird here, I'm going to set this equal to this fraction that we're going to use to solve for the grams of nitrogen for a total of 35 grams of this molecule. Now, where did this number come from? Because this is kind of weird. Remember, I said I want you to assume that we have a 100 gram sample. If we have a 100 gram sample, 35% of that 100 gram sample is coming from this guy right here. 35% of 100 is 35 grams. So in a 100 gram sample, we have a total of 35 grams of ammonium phosphate. That's where this comes from. Like I said, this is hard. So we're going to use this equality, cross multiply, solve for X. I'm not showing you the math on that because you've seen it 3 times. But this is solving for X. Now, because I also have nitrogen in my second component, I've got to do all of this again. So down here, for this one, I have only 2 nitrogens in this molecule, so 14 times 2, because I have 2 nitrogens. This is the total mass of the calcium nitrate. Added up the mass of the calcium, the nitrogen, the oxygen, I got 164. I want to figure out, I'm going to set that equal to X over 21. Again, where did that come from? We're pretending like we have a 100 gram sample. If we have a 100 gram sample, 21% of 100 grams, 21 grams, that's the total mass of calcium nitrate, and I'm solving for X again using the cross multiplication rule. Now, if you have a third compound that has nitrogen in it, you would need to do this process a third time down here. So what I have done is, I have calculated the mass of nitrogen coming from ammonium phosphate in my 100 gram sample. I have calculated the mass of nitrogen coming from calcium nitrate in my 100 gram sample. This is the total mass of the nitrogen. I'm going to add those up. That's the total mass of the nitrogen in my 100 gram sample. This particular problem, ALEKS is asking us for a percent. So I'm going to take the total mass of nitrogen divided by the total mass of my 100 gram sample, and that's going to give me 13.46%. Okay, one more. And this one I think is absolutely the hardest one out of all of them. This one, there's so much going on in this problem. So this one is saying that we have the Earth. The Earth has a crust on it, and then, or the outer surface is the crust, and then there is this atmosphere. It wants us to calculate the relative ratio of oxygen in the Earth's atmosphere relative to oxygen in the Earth's crust. Oh my gosh. So there's a lot of stuff that we have to do. We're going to take this one piece at a time. With all the versions of this variation of the problem, all the variations that I've seen, the variation comes right here in this number. So, because I'm seeing like some pretty consistent numbers for the rest of it. Double check your numbers. Because I didn't look at a ton of versions of this problem, but it looks like this is where ALEKS varies the problem from one to the other. So what we're going to do is start by calculating the amount of oxygen in the crust. And to do that, we have to figure out how big the crust actually is, because it gives us the radius of the Earth, and then it tells us that the crust is the upper 75 kilometers of that radius. So I'm starting by sketching a little picture of the Earth with the radius, and I am going to use the equation for calculating the volume of a sphere, because the Earth is a sphere, and I'm going to calculate the volume of the Earth from the radius that was provided to me in the problem. There it is right there. Now that is the volume of the whole entire Earth. The problem is telling us that the crust is just the upper 75 kilometers of the Earth. So the rest of the Earth, all the rest of this stuff on the inside, we are not taking into consideration in this problem at all. So what I need to do is figure out the volume of this inside part, and I need to subtract it from this total volume right here in order to get the volume of the crust. So again, I've got the whole entire volume of the Earth, that's this. I'm going to figure out the volume of the not crust, and I'm going to subtract that from this volume. So here we go. Here's the inner part of the Earth, because it tells me that the crust is the upper 75 kilometers. So the inner part is the radius, the whole entire radius of the Earth, minus 75 kilometers gives me the radius of just the inner part right there. So this number was not given in the problem. I figured it out from subtracting 6,371 minus 75. From that, I'm going to calculate the volume of the inner part, and we're going to use this later. Don't worry about that right now. And I'm going to subtract the volume of the Earth subtract the volume of the inner part from the volume of the Earth to get the volume of the crust. So the volume of the crust is going to be the volume of the whole entire Earth minus the volume of just the inner part. And that is, for me, that is 3.5 times 10 to the 10 kilometers cubed. Now I can use the density. It's giving me the density of this compound in the crust. It's giving me the density, and I can use the density to calculate the mass of the crust. The density is unfortunately in grams per cubic centimeter. I calculated the volumes in cubic kilometers, so I need to do a unit conversion. There's my cubic kilometers. I'm first going to convert that into cubic meters, and then I'm going to convert it into cubic centimeters. Here is my volume of the Earth the volume of the crust in units of cubic centimeter. From here, I'm going to multiply by the density of the crust in order to get the mass. There it is, 8.75 times 10 to the 25. And your number may be a tiny bit different because you may not have a 75 kilometer thick crust. Now it's telling us to assume that this whole entire mass right here, it tells us assume the whole entire mass is this KALSI308. So this is where now the problem is going to start to look a little bit more familiar. That is the total whole entire mass. What we are trying to do, remember in this problem, we're trying to figure this ratio of oxygen out. So what we want to do here, just like we've done for previous problems, is to figure out the mass of oxygen relative to the mass of the crust. There are 8 oxygen atoms in this formula, so 8 times 16, that's the total mass of oxygen. The molecular weight of the whole entire thing, potassium plus aluminum plus 3 SIs plus 8 oxygens, that's going to give us a total mass of 278. This is the ratio of oxygen to KALSI308. This is the total mass of KALSI308, how much oxygen is there. So we've got it, kind of boiled down to a very similar looking problem, similar to the last 4. This is going to allow us to calculate the mass of just oxygen in the crust using that crisscross rule again, and then solving for X. I'm not showing any of that math. I'm just jumping straight to X, 4.03 times 10 to the 25. That is the mass of oxygen in the Earth's crust. That's not even what the problem is asking us for. We now have to figure out the mass of oxygen in the atmosphere. So the atmosphere is around the Earth. It's telling us that the radius of the whole entire atmosphere is 6,471, at least in my version of the problem. I know that because it says that the atmosphere is 100 kilometers thick over the surface of the Earth. So I took the radius of the Earth plus 100 kilometers, and that gave me the radius of the atmosphere. I used the volume equation to calculate the volume of the atmosphere. Now, again, I got to keep in mind that the atmosphere is not this whole entire sphere. The atmosphere is, the Earth is inside this sphere. So to get the actual volume of the atmosphere, I need to take this giant sphere and subtract from that the volume of the Earth. The volume of the atmosphere is the volume of the whole entire giant sphere minus the volume of the Earth. Similar to what we did over here. That's 6 times 10 to the 10 cubic kilometers. Before you get crazy with the unit conversions, notice that this one is giving us a density in units of grams per cubic meter. So this time we need to convert cubic kilometers only into cubic meters. So we're just going to be doing this much of the unit conversion. We don't need to do this part. I didn't write it out. I just did the math. This number times 10 to the third cubed gives me this number right here. This is the volume of the atmosphere in cubic meters. Now we're going to use the density to figure out the mass of the atmosphere. Multiply it by the density. Those cubic meters cancel. There's the mass of the atmosphere. Now, this part is actually a little bit easier because it does tell us that the atmosphere is 23.1% oxygen by mass. So we don't need to use one of these kind of setups. We already know that this mass right here, 23.1% of it is oxygen. So we're going to take this mass and multiply it by 23.1%. There's the mass of oxygen in the atmosphere. Okay, so we're almost done. This problem wants the ratio of oxygen in the atmosphere, that's this number right here, per oxygen in the Earth's crust, that's this number right here. We're just going to set that up like a fraction. Atmosphere over the crust, oxygen in the atmosphere over oxygen in the crust, oxygen in the atmosphere over oxygen in the crust. I get a pretty small number, 3.4 times 10 to the minus 7. Good luck with this problem. It is really hard.